Okay, welcome to another session of Intro to Photonics. So the last couple of lectures we've been looking at some more examples of wave optics, some specific properties in wave optics, including multiple slit interference, and then the last lecture we just introduced the concept of coherence, right. So we looked at what temporal coherence is all about. So we towards the end of the last lecture we were examining certain examples for sources, and we said okay, sunlight is a source, it's a light source, right. But when you look at the spectral width of sunlight, and especially we are just looking at picking up the visible region, and that is quite broad. So the result that the coherence time or the coherence length is quite short, right, as opposed to helium neon laser, which has a so-called single frequency operation, but the line width can be in the order of megahertz, in which case we found that the coherence length is rather high. So, what are the uses of something like this? If you are building an interferometer, right, in general you would say, okay, what do you want, longer or shorter coherence length? Huh? Shorter. Why would we need shorter coherence length? There is actually one good example of that, I will come back to that, but in general you want to have longer coherence length so that you do not have to match the path lengths so accurately, right. So, for example, with the LED we are saying the coherence length is 20 microns, so that means both the path have to be matched to 20 micron accuracy, so that you can have interference, right, and that is very, very hard to do, whereas if you are trying to build an interferometer with a 300 meter coherence length, you could roughly put the two mirrors at some certain distance, and chances are that you will get good interference, right. So if you want to build an interferometer, you are typically looking for long coherence length, and that is actually what is behind, we heard of the LIGO. Huh? So what is LIGO? LIGO is basically a project which is looking at detecting gravitational waves. You heard of gravitational waves recently? The Nobel Prize recently was given for the detection of gravitational waves, and believe it or not, that detection was through one of these interferometers, a Michelson interferometer configuration, okay. And there since the gravitational wave, the wavelength is fairly long, you need to have a very long interferometer. How long is long? So one of the interferometers that I know of is 6 kilometer long arms, 6 kilometers, okay, and just so that you do not have any external perturbations, the entire thing is maintained under vacuum conditions, a lot of precautions taken, it's something that's buried underground and so on. So, but the point is, if you are making a 6 kilometer long arm, so you have two arms, each of those 6 kilometers long, you would want to have here and there some leeway in terms of positioning the mirrors, right. So clearly in those sort of applications it helps to have a highly coherent source, highly temporally coherent source. So you have a fairly long coherence length, right. So that certainly helps in those sort of cases. But somebody mentioned maybe you want to have short coherence length, and that was still quite useful in an application called optical coherence tomography, or in short OCT. So, how would this help in optical coherence tomography? Well, using optical coherence tomography, what you are trying to get to is a fairly accurate investigation of what is happening, let us say, in the eye. Okay, in the eye you want to look at every 10 microns, you want to take slices of 10 microns and see what is happening. So, how do you localize this investigation to 10 microns? Well, you can essentially, let us say we have a Michelson interferometer like this, and in this case I am just going to erase little bit of this and say over here what I have is a sample where I need to get 10 micron resolution. I want to characterize this sample with 10 micron resolution. So, what do? I initially start with D1 and D2 being equal. Okay. So, I start with, for example, this layer over here. Okay. So, I position my mirror so that I am essentially looking at only this layer. Why? Because anything outside of this layer has got a different path length. I do not have the coherence to support interference. Okay. I am getting interference fringes only from that layer at any particular time. Okay. Now, how do I go to the next layer? What can I do to go to the next layer? Change D1. So, I would basically I would move this mirror, move by 10 microns, and then what am I looking at in that case? If I increase that path length by 10 microns, I am looking at this next layer, right, and then I move by another 10 microns, I am looking at the next layer, and so on. So, I can limit my interference to only this 10 micron at a time, provided what? What should be the nature of my source? It should have very low coherence length, right. What does that mean? Low coherence length is supported by a source with very large spectral width. Okay. So, if I have a LED source over here, okay, if I use LED source, a broadband source like that, then I can get information from each slice of the sample. So, this is my sample, like I said, it could be your eye, for example. You are going for a eye testing, the doctor wants to see layer by layer how your eye is, they can put you through an OCT and get all that information. Okay. And it is actually a commercial device equipment right now, but something once again as advanced as this has a very fundamental principle based on interference of light. You are specifically building this Michelson interferometer, you are specifically using a low coherence source, and then you can do something as accurately as this. So, what I want to actually do is time permitting work out a couple of problems related to the concept that we have looked at so far. But before I go to that, I want to give you an idea of what spatial coherence is all about. To understand this, let us just go back to your Young's double slit experiment, okay, wherein we said, okay, you have these two wavelets that are generated when you have this plane wave that is incident on it, and then in the distant observation point you are actually seeing constructive and destructive interference, right. Now, suppose I have this source coming at a slight angle over here, okay. It's not at the it's not normal to the pinhole, it's coming at a slight angle. Where do you expect the interference fringes to be? What will happen to the interference fringes? It will get dislocated, get shifted. So, now the interference fringes will be like this, right. Similarly, I can come in with if I come in with something like this, then it will be shifted down. So, the corresponding interference fringes will look something like this, right. So, effectively, if your source has multiple wave vectors, okay, wave directions, you get an interference fringe that is effectively smudged, okay. Or in other words, when you look at this interference fringe, so you are basically looking at some average value, and previously you were going from 0, let us say we are plotting I over 2 times I naught, right. We are plotting over 0 to 2, right, it was going from maxima to minima and so on. But now, so this is as a function of the path length difference or phi, right. But now what happens is, you do not have that much of, you cannot go to maxima and minima, because minima is, if you have a single wave vector, the minima is clear, maxima and minima are clearly defined, like it is for the red. But if it is got multiple wave vectors, then that maxima and minima definition is changed. So, effectively what you see is something like this, which is with so the maxima is not the highest you can get, minima is not the lowest you can get. So, effectively your the visibility, the contrast of your fringes reduce, right. So, the contrast essentially is getting reduced. So, why am I talking about all of this? Because when you look at practical light sources, okay, most of the light sources that we have will essentially not be absolutely planar, okay. So, you would have a wave front like this, and this wave front, if you decompose, will consist of this wave front plus this wave front plus this wave front, okay. So, it will consist of all these different wave vectors, okay. And if it has all those wave vectors, then your visibility of the fringes is reduced, okay. So, effectively what we are defining here is another coherence term, okay, which depends on the spatial properties of the light that we are looking at. Okay. So, previously we were looking at for temporal coherence, you were looking at u of t plus tau. So, you were looking at a point in one correlation between a point in one wavefront with another wavefront, a delayed wavefront. You are looking at the correlation between those two, but here you are looking at the correlation between 2 points in the same wavefront. Okay. So, you are looking at basically u of r1, u of r2, the correlation between those two, okay. And that is actually the spatial coherence function is defined by this, okay. So, in general, when we are looking at partially coherent sources, you say I is nothing but u1 plus u2 the whole square, time averaged of that, and that we can write as u1 square time average value plus u2 mod square time average value plus u1 conjugate u2 plus u1 u2 conjugate, right. So, this is what we have seen before, and that we have previously said, okay, that is equal to I1 plus I2 plus this time average of u1 conjugate u2 is what we have defined as your coherence function. So, G12 plus this will be G12 conjugate, okay. Any complex value and its conjugate, if you add them together, that is going to give you I1 plus I2 plus 2 times real part of G12, right. So, and then that you can write it out as I1 plus I2 plus 2 root I1 I2, which is the same as what we did before. Real part of G12, where G12 is what? Small g12 is the degree, the normalized value, right. So, that is the degree of coherence, okay. And this is what you can write out as 1 plus I1 plus I2, 2 root I1 I2, magnitude of G12 cos of delta phi, right. So, what we have done here is, with respect to our previous discussion, what is the new thing here? So, we have this factor also come into the picture, and that factor, if you look closely at it, that will be this fringe contrast, okay. So, that is actually the degree of coherence provides this fringe contrast. We had been looking at the ideal case before, the ideal case of plane monochromatic wave, right, and in which case G12 was equal to 1. So, we had these constructive and destructive interference yielding maxima and minima, which is the absolute maximum and absolute minimum, which is 0, right. So, that is what we were going, but now we are bringing into the discussion a property of light called coherence of light. One part of that is spatial coherence, which we have defined over here, and the other part of it is temporal coherence, where which is related to looking at the relative autocorrelation, right, between two wavefronts that are delayed with respect to each other. Okay. So, this is temporal coherence, which is dependent on what? The temporal coherence time is inversely proportional to the spectral width, and in this case with spatial coherence we will define a coherence length, a coherence distance, which is given by lambda over theta s. Okay, that coherence is given by lambda over theta s, where theta s denotes the angles subtended by the source. Okay, the angle subtended by the source. If it is a plane wave, what is the angle subtended? 0, right. If it is an absolute plane wave, the angle subtended is 0, but if you have a non-planar wavefront, that wavefront can be decomposed into superposition of multiple plane wavefronts with different angles. That angle subtension is what we are looking at as theta s. So, if you have more angle subtension, let us take the example of sunlight. It's not only temporally incoherent, but spatially also it subtends a large angle, or LED for example. LED, I mean, why do we use LEDs for these lights here? Because the emission subtends over a large angle, right. So, that means you have multiple wave vectors that are constituting this thing, and hence this LED will be spatially incoherent also. Okay, it is not just temporally incoherent. Temporal incoherence comes from the perspective of large spectral width, but spatially incoherent because of this. Now that I said that, can I improve the spatial coherence of light? Let us say I take a very poor spatially coherent light, right, and can I improve the spatial coherence? Can I do that? Yes, no? Maybe you are not sure. It turns out yes, you can. So, what happens when you take a source like this and put it through a lens? So, you are actually looking at an spatially incoherent source and you are putting it through a lens, then what you will see, and of course I am not giving you all the details to appreciate this, but what you will see is that it will come to a focus, but it will not come to a focus at one particular point. If it was a planar wavefront, you would have this come to a focus at one particular point, but if it is a non-planar wavefront, it will not only have a focal point here, but also things here and so on, right. It will have multiple spots, because like I said, you can decompose it into multiple plane waves, that are slightly at a different angle with respect to each other, and with respect to that angle when you are focusing you will get different points at which light is focusing. Okay. Now, if I put a spatial filter, right, I put a pinhole and such that it allows only that central point. That central point constitutes a wave front, a wave vector that is going in a particular direction. So, this will go through a particular direction. Now, of course, you would say that it's going in a particular direction, okay, but it's not a plane wave front, it's a spherical wave front, right, because what's coming out of this pinhole, you would say through diffraction it will go like this, right. But any well defined spherical wavelength, I can always find some way of compensating for that wave front. What will I do? I will put a lens here that compensates for this divergence, and what I get out of here is a plane wave front. Do you understand this? Right? So, if you have picked one particular wave vector, okay, even though it's diverging, it will have nice spherical wave fronts which can be corrected if you can put a lens in front of that, that straightens out all those wave fronts, that delays this part of the wave with respect to the other part, and then you can straighten out the wave front. So, what I get out of this is nice plane wave fronts. What do I lose in the process? I made the source spatially coherent, but what do I lose in the process? Intensity. All the power that's present in these other wave vectors, I am losing those, right. So that's what you have to do. So, to clean up the beam, so you can take sunlight for example, and you want to make sunlight spatially coherent, so you can put one of these spatial filters in place and take out all these other higher spatial frequencies, and you get one particular spatial frequency out through a pinhole. And that pinhole, what should be the size of that pinhole? That size has to be comparable to the wavelength of light, because that spot size will be comparable to the wavelength of light. So, it's got to be a very narrow pinhole in the order of microns, okay, and then only you can do this. Now that I told you that, can I ask this other question? Can I improve the temporal coherence of light? What do you think? Can I improve the temporal coherence? Yes. I mean, if I can find a filter to do the spatial coherence, I can find a filter to improve temporal coherence also. All I do is, okay, I have all these multiple frequencies, I put a filter and I get only one frequency out, or only a very narrow band of frequencies out, okay. And within the, when you look at that narrow band of frequency, that is going to be temporally coherent, okay. So, you get sources which are not spatially coherent, not temporally coherent, but if you want to achieve a particular functionality, you could do things to improve the coherence of light, okay. But if you know why, or if you know, if somebody tells you it's not spatially coherent, then you say, okay, what is the angle subtended by this, and I can find a way, I can put a spatial filter, I can improve spatial coherence, or I can put a spectral filter, I can improve the temporal coherence. Okay. Okay. So, I do not have a whole lot of time, but in this session, but what I can quickly do is give you a feel for how these principles that we have learned so far, we looked at multiple beam interference and then these properties of temporal and spatial coherence, how these principles can be used to design optical elements, optical instruments. Okay. So, let's start with example 1, and I think we will have to continue this later on, but we will at least get started. Let us start with the example of interference in thin films, which actually constitutes multiple layers. Okay. So, what is this based on? Now, whenever light goes from one medium to another, okay, let us say a nice plane wave is coming and hitting this interface, okay. What do you expect to happen? So, can undergo refraction, but in this case normal incidence. So, where do you think it is going to go? Go in the same direction, right? It is going to go straight down. Is that the only thing that happens? There will be a reflection also, right? So, that reflection, if you want to quantify that reflection coefficient R, what is that going to be based on? That is going to be based on the relative refractive indexes of the two media, right. If you were talking in terms of electromagnetics, you learnt in electromagnetics that the reflection coefficient is eta 2 minus eta 1 divided by eta 2 plus eta 1, right, where eta 2 corresponded to the impedance of the second medium, that is the medium that is going into, and eta 1 corresponds to the medium where the wave is originating, right. But eta, the wave impedance as they call it in electromagnetics, is nothing but mu over epsilon. So, it is inversely related to root of epsilon, and I would say that root of epsilon r, the relative permittivity, is nothing but the refractive index of a medium. Okay. So, maybe you have not heard that before, but I just tell you that root of that relative permittivity is nothing but the refractive index of the medium. So, we are going from whatever we learnt in electromagnetics to what we want to do in wave optics. Okay. But if you substitute all these terms, what you will basically find is, if mu is the same for both regions, then you get n1 minus n2 divided by n1 plus n2, right. Whatever we learnt in terms of wave impedance, we are just bringing it into in terms of the refractive index. Okay. So, what does that tell you? Especially if n2 is greater than n1, you are going from a rarer medium into a denser medium. What does R become? R is negative, right. What does a negative reflection coefficient mean? You have a wave that is coming and hitting this interface, which is giving you a negative reflection coefficient. So, what does that mean? the wave essentially gets flipped, right, or you have a pi phase shift. You have a pi phase shift whenever a wave is going from a rarer medium into a denser medium. Okay, and of course, if it's going from a denser medium to a rarer medium, there is no phase shift. There's just zero phase shift, right? But when you're going from rarer to denser, you undergo a pi phase shift. Okay, so we are going to track as light goes through multiple layers. We are going to track how that light wave is going to accumulate phase, and we are also going to track how the reflected components, when we look at reflection from this multiple layers, if you have multiple layers, how these reflected components, whether they are going to come in phase over here or out of phase over there, and so on. In certain examples, you need them to be out of phase. One popular example is what I am wearing here. These glasses, they are anti-reflection coated. Some of your glasses, I see some of you wearing glasses. When you go to the guy that makes the glasses, he asks whether you want an anti-reflection coating, and you say yes. So what goes into putting that coating on this, right? Anti-reflection basically says, okay, whenever light goes from one medium to another, there is always reflection. So if I am putting my glasses, you will see reflected light, you won't see my eyes, right? So you want to have anti-glare filters so that that reflection is frustrated. So how do you frustrate that reflection? Destructive interference. Whenever you are talking about frustrating something, you are looking at destructive interference, making that reflection component zero. Okay. So you may have applications like that where you are looking for destructive interference because of reflection from interfaces. You have applications where you want to reflect light, like when you are doing this experiment, the Michelson interferometer, you put these two mirrors. What are these mirrors? They could be dielectric mirrors, they could be metal coated mirrors, but they could also be dielectric mirrors. In that case, you want all the reflected components to be doing what? Constructive interference. They should have constructive interference, so they all add up and it give you a very high intensity light coming back. So we are going to look at those examples. We will do that in the next session because we run out of time here. Okay, thank you.